What up, calculus students? You can see my face in this video because I'm getting all fancy with it. What I wanted to do was take the time to introduce our introduction to chapter 3. So far you've learned how to find limits. Hopefully, in theory, you've learned how to find limits. We've learned what it means for a function to be continuous. That basically means fingers are coming together and there's no holes, there's no jumps, there's no asymptotes. That's continuity. And those concepts are now solid enough for us to move into the third concept of this class, which is the derivative. This video is going to really mainly walk you through several demonstrations to help solidify the concept of rates of change. Average rate of change as opposed to instantaneous rate of change, what they mean when you're looking at a graph and how to find both of them. That's what this lesson's for. Your homework is to copy down the notes for the first 2 pages of the outline you printed out, as well as complete that GeoGebra activity, that second handout you were supposed to print out. And there will be a second video explaining how to use GeoGebra so you can complete that activity. So without further ado, let's begin. For our first demonstration, we're going to consider the scenario where a bundle has been dropped from a helicopter. So I'm going to go ahead and just put my bundle up here, and we're just going to call that bundle A. And maybe what I'll do is change this so I can see the value of A on the graph. So the bundle started at 400 feet above the ground. I know that because it's telling me here that its height in feet, f of x. So f of x, as we know, are the y values. So the y value is the height in feet above the ground. X seconds, so I know that this x coordinate right now, which is 0 for A, is referring to the seconds after it has been dropped. So 0, that must be right when it's dropped, is given by this equation, f of x equals 400 minus 16x squared, which we also see over here. So basically the bundle starts off at 400 feet and then it basically begins to drop. So as time is ticking, as you can see, the x coordinate is going more and more toward 5. The bundle is heading straight for the ground. Okay, so that's our scenario. What I want to look at are rates of change. How fast is this object falling? I can see how high it is at a given time, but what I want to know is how fast is it falling between, say, 0 and 5 seconds. So I'm going to introduce another point onto this curve, and we'll call that point B. And so right now I have B is a little further along. Let's go ahead and show the labels for B on here. So B is closer to the ground. A is up here at 400, B is closer to the ground. So let's consider A now the starting point of this bundle. This is where the bundle started, so we can just sort of keep that visual in mind. B is where the bundle is at now, let's just say, at a given time x seconds. So let's say I wanted to find the rate of change. How fast is this bundle B falling at 2.1 seconds? I'll just use this point, 2.1 seconds. Well, the tools that we have available to us to help us find rates of change is basically just to figure out how far has it fallen over how much time has passed. So our application for that is called a secant line. A secant line is a line that intersects a function at 2 points, just like the one I'm showing you here. So as you can see, the average rate of change would basically be the slope of this secant line. It'd be the change in y over the change in x. Y, of course, being height, change in height, over x being change in x being the change in time. What that finds is basically the slope of this tangent line. So let's say I wanted to find that slope. I would just look at my rise, which is of course going down here. And the way I do that is I would subtract my y coordinates. So I would do 329.54 minus 400. And that value gives me negative 70.46. So that's my change in height. The object fell from 400 feet to 329.54 feet, so that's a drop or negative value of 70.46. That's my change in height. Then I would go ahead and find my change in x, which is the change in times from 0 seconds to 2.1 seconds. So that's a positive change because time was ticking forward into the future. So that's a positive change of 2.1 seconds. And then, as you know, we would basically take those two numbers and divide them. We would do change in y over change in x. That's how we find the rate at which this object is falling on average. And so when I do that, I get negative 33.6. And it's negative because the object's falling. So that would be feet per second, because it dropped this much feet, 70.46 feet, in a period of 2.1 seconds. So this negative 33.6 is in feet per second. That's a rate of change right there. How many feet did it drop in how many seconds? So that's how quickly it's dropping on average. Now the reason I say on average is because that's the slope of this line. But if you look at the curve itself, it did not have a constant rate of change. Up here at the top, it wasn't really falling that fast, and as you move toward point B, you can see that the rate of change is actually going a little bit, it's dropping a little bit faster. So the curve itself is not moving at a constant rate of change, but all we have available to us at this point is algebra, which if we are given 2 points on the curve, A and B, I can then find the slope of the line connecting those 2 points quite easily by subtracting the y values and then dividing that by the difference between x values. So that is how we find an average rate of change. And here we'll go ahead and verify that. This one, yeah. We'll go ahead and verify our slope there of this line. And yeah, it's about negative 33.6. We can see that. Change in y over change in x. Okay. So, supposing I wanted to find exactly how quickly it's falling here, and not just an average rate of change, because if you look right along the curve here, it looks like it's going down a lot faster than this line is going down. This line is just kind of gives us overall between this point 0 and this point 2.1 how quickly it was falling. Well, what I could do is I could have this point A, and I could try and move it closer. I could try and shorten that interval. And if you look, it looks like my line now is a very close approximation of the actual curve. So I can see it's actually decreasing at a much quicker rate. In fact, if I wanted to find the slope of this line, I could see that it's decreasing at a rate of negative 61.4. So it's a lot faster than what I had originally found by using the average rate of change. Because as we can see, the rate of change along this curve is not constant. So using average rates of change helps give us an approximation. And if we can close the gap between the 2 points that we're finding the average rate of change of, we can get a much, much, much better approximation. And our goal is to try and get to the point where there'd only be 1 point. But as you can see, suddenly my line disappeared, and it wasn't able to find a slope. That's because in algebra, we're somewhat limited. We need 2 points to be able to find the slope of a line. And so you'll see this is where calculus is going to come in. Calculus is going to come in and help us to find the slope of that line that should be there right when it disappears, and we call that line the tangent line. So let me back A up here. Let's get as close as we can. It looks like the rate of change at point B is about negative 65.5. Let's see if I can get a little closer. Okay, maybe negative 66.7. Okay, that looks like a pretty good approximation. And that's with a teeny tiny interval between the points A and B. So now I'm going to go ahead and get rid of point A. And now we just have point B. And now let's go ahead and get a tangent line at point B. And see if we can get that slope. So that slope is actually negative 67.2. We were pretty close in our approximation. So algebra can get us there pretty close. It can give us a pretty close approximation to the instantaneous rate of change at point B. And if you can see this tangent, if you look at just point B, so if I were to zoom in here on just the point B, it's almost hard, the closer I get, to even tell the difference between the curve that point B is on and then this line tangent to the curve. And that's why the slope of the tangent line gives us the actual exact slope of the tangent line at point B. So I'm going to go ahead and zoom back out here again. The average rate of change, we need 2 points, and it can tell us an approximation of that change. But the instantaneous rate of change, we need the slope of the tangent line, and we're going to need calculus to be able to take us there. So that brings us to our notes portion. So what I'm going to do now is give you a formalized definition and formula for the average rate of change. So first, we have a curve, and let's just go ahead and call that curve f of x. And for this average rate of change, we're going to need 2 points along that curve. So let's go ahead and call those 2 points A, comma f of A, and B, comma f of B. So f of A is just the y value evaluated when x equals A. And f of b is just the y value evaluated when x equals b. So x comma y, x comma y. So I'm just going to go ahead and use the same sort of image from the last video we watched. Just, I believe the consistency helps connect the concepts. And we had this downward facing parabola. And we had a, f of a was right up here. So I'll go ahead and call that our a, f of a point. And then we had another point sort of further down on the curve, and then that was our b, f of b point. Okay. And what we were trying to do was find the rate of change of f of x, the rate of change of the curve on average along this interval from a to b. So here's my interval of x values from a to b. Well, it turned out that the way we found that average rate of change was by looking at the line that connects those 2 points. And we called that line the secant line. So just as a reminder, secant line is a line that intersects a curve or a function at 2 different places. That's the secant line. And then the average rate of change was determined by finding the slope of that secant line. And so we basically just found the change in y, which we'll call f of b minus f of a, and then we divided that by the change in x, which we'll just call b minus a. And so that's the formula for average rate of change. And what you need to remember is that's a synonym for slope of the secant line. And maybe it would even be additionally helpful to kind of think back to Algebra 1 when we used to do y2 minus y1 over x2 minus x1, and just notice it's the exact same thing. We're using our function notation because we're a little bit more advanced being in calculus, but this is y2, it's the second y coordinate, and this is y1, it's the first y coordinate. This is x2, it's the second x coordinate, and then this is x1, it's the first x coordinate. So it's just change in y over change in x, which is the slope of the line that goes through the curve at those 2 points, which we call the slope of the secant line. Okay, so that's algebra. That's all fine and good. We're all happy, la la la. But we have a bigger task at hand here. Supposing I want to find the slope of the line, or excuse me, suppose I want to find the rate of change at just that point B, like instantaneously at point B, not the average rate of change on the interval. So I should probably put that here. This is the average rate of change. Go ahead and add a little part up here, of f of x on the interval from a to b. So an average rate of change is going to rely on an interval. But supposing I want to find the instantaneous rate of change at one particular point. Well, that's where calculus, we need calculus. Algebra is unable to do that for us. Now in the video or in the demonstration we saw that an instantaneous rate of change when you look at a graph is the slope of the tangent line. And the reason why that presented a problem is because a tangent line is a line that intersects a function at just one point. So again, let's take a look at this image. So let's have that point there. A tangent line is a line that would intersect the function at just that one point. It doesn't intersect it at another point, just that one point. And if you zoom in right where the line is tangent to the curve at the point, it is very hard to tell the difference between the line itself and the curve. So that line is telling us the exact rate of change at which that object is falling or changing, or whatever the situation may be, at that particular point. Okay, so let's go ahead and for this, I'm going to call this A for this demonstration. Okay. Now, what we did in the demo is we basically took that other point, which I'll just go ahead and call that other point. I want to be a little bit more general here. Instead of calling them A and B, I'm going to have X and A. What we did is we slid that point X toward the point A. And as we did that, the secant line, which this secant line would start off something like that, that secant line, as we slide X closer to A, would become more and more like the tangent line, and they would begin to share the same slope. So here's how we use calculus to make that happen. We begin by finding the change in y, so the change in f of x and f of a, divided by the change in x. Just like up here. Instead of f of b minus f of a, b minus a, we have f of x minus f of a, x minus a, and that just allows us to be more general, so this is allowed to be a variable. In other words, I could place this here, I could place it here, I could place it wherever I want, and have it slide toward this point in either direction. And we're going to take the limit of that. So here's where the calculus comes in. So we began with algebra, just finding the slope of the secant line, but we take the limit of that slope as x, the x coordinate of whatever point I've chosen, approaches A. And what that does, what this calculus does, is allow us to slide these 2 points together until they overlap. It allows them to slide together until they overlap. And this right here gives us the slope of the tangent line. It has to have the limit though. Without the limit, it's just the slope of the secant line. That is the slope of the secant line. This, the calculus, sliding the 2 points together until they basically become the same point, that's the slope of the tangent line. Well, in calculus, this is referred to as the derivative. That's what the derivative is. It's the slope of the tangent line. And so the notation I'm going to use here, when you look at this, it's a little tick mark there, I guess you could say, and this is called f prime of A. F prime of A, or you could say the derivative of f at A. F prime of A. Derivative of f at A, which is the slope of the line tangent to the curve at A, or the instantaneous rate of change of the curve at A. So this is kind of what we call the derivative at a point. It's very specific. This A is actually a number. It's not allowed to change and be a variable. But I wanted to begin with this version of the formula because I think it's very helpful to see the connection between the slope of the secant line, which is when you have two particular points and you find change in y over change in x, and that helps find an average rate of change of a function, and then seeing how similar that is and how we really use the same thing. We still do change in y over change in x, but we slide those points together to the point where they overlap essentially, and we end up with just one point and then one tangent line that's going through the curve at that point. And that's called the derivative. The slope of the tangent line is called the derivative. It's also referred to as the instantaneous rate of change. But I do need to formalize that a little bit for you and show you the formal definition of the derivative. And this is not just at a point, this is at all values of x. So I'm going to go ahead and call this f prime of x, not f prime of a now. This is a derivative that can be used to find the instantaneous rate of change at any point x. So x is a variable, meaning allowed to change. So the formula goes like this. Well, first you would begin with the slope of the secant line as usual. So you have the change in y, which in this more general form is going to be called f of x plus h minus f of x, all over the change in x, which is simply h. Let's talk about that for a second, and then I'll finish the rest of this formula. So what we need to understand here is that the 2 points are x comma f of x and x plus h comma f of x plus h. So it's like this original secant line up here, but instead of a f of a and b f of b, it's x f of x and then x plus h comma f of x plus h, because these are two changing points depending on what x is. H is just the change between the different x values. So for example, let's say I have this curve. Let's go ahead and let that be x, and then h is just some distance that I move to get to another x value. We'll call that x plus h. Some distance that I would move to the right. Up here, this height up here would be my f of x, and then this height over here would be my f of x plus h. It's just the height evaluated at that like further along x coordinate, which was h units away from x. And so again, what I'm finding here is just the slope of the line that connects those 2 points, and I just subtract f of x plus h minus f of x to find the rise, and then I subtract x plus h minus x to find the run. And if you look at that subtraction, x plus h minus x, you'll notice that the x's cancel out, and you're simply left with h, which visually makes sense because that was the distance between those two x coordinates. Okay, but again, that's just the slope of the secant line. What I'm trying to do here is find the derivative, which is the slope of the tangent line. And so to do that, I use my calculus that we have now learned, limits, and I take the limit of that secant line. So I'm taking, the limit of the slope. This is the slope of the secant line. I take the limit of that slope as h, which is the change in x, approaches 0, which means the change is decreasing. And we saw in the last demonstration that when the change decreases, the points then become 1 point. The 2 points then become 1 point. This would slide this way and join this point here, and then you would just have one line tangent to the curve at that 1 point. And that line would look something more like this, because it'd be tangent to the curve at that point. And as we slide those 2 points together, that's how we get the slope of the tangent line, which is also the instantaneous rate of change, which is also the derivative of the function at x. So let's look at another demonstration to help us visualize this definition of a derivative and really solidify that. So this demonstration is to help us see how the second definition, the formal definition that I showed you, is really the same thing as the first one. So it's really just a secant line slope becoming a tangent line slope. So take a look at what we have here. We have a portion of the graph y equals x squared. We have a point Q, which is up here, 2, 4. So 2 is like our x, and 4 is our f of x, because if you plug 2 into the function f of x, you square it, you get 4. So 4 is f of 2, or f of x. Point P is some distance away from point Q. In fact, to be specific, here's my h. I don't know if you can see that, it's really light. But h is this distance between 2 and 5. So they have here h is equal to 3. And so I can see that this x coordinate here is basically x plus h. So here's my x plus h, because it's 3 units or h units away from the first x coordinate of 2. And then the 25 is my f of x plus h, because if I plug 5 into the function of x and square it, I get 25. So this is x and f of x. And this is x plus h and f of x plus h. And up here I have a little slider that's going to let me have h approaching 0. So right now, if I ignore the red line and just look at this really light sort of beige line, that is slope of the secant line. The slope of that line would be f of x plus h minus f of x divided by h. Okay, but what I'm going to do is take the limit of that as h approaches 0, meaning the change between x diminishes, decreases. Look at my h value. Watch the h value. It's 1.1, 9.8.47, whatever. It's heading down toward eventually 0. Of course, they're not letting it get exactly 0, because if I was exactly at 0, then I'd be dividing by 0, which opens up a whole nother can of worms. So I let it approach 0. And when I do, Q and P essentially become the same point. See, I have point Q is 2.4, and then point P is 2.0001 and 4.004. They essentially become the same point, and now my secant slope is identical to the tangent slope. And so it's the same idea as before. I have the point that was h units away. So originally P was 3 units away from Q, h units away. As I make that h, or that change in x, that distance between x diminish, as I make it go to 0, that forces point P to slide down the curve to point Q, because both Q and P are on the same curve. So as I make the x values get closer together, so I'm trying to make this x value get closer to 2, it forces the y values to get closer together, and the point slides down, and eventually we're looking at pretty much the same point. And so now my line that's going through those points, which is really one point now, is now tangent to the curve. And so now I'm able to find the instantaneous rate of change of this function at point P. Or I'm able to find the slope of the tangent line at point P, or the derivative of the function at point P, now that I have taken the limit as h approaches 0. We can take another look at that. Here's the square root function, like I referred to as the eyebrow graph, and again I'll have my h start all the way over here. So now my distance between x is 15. So now my h is 15, because my original x value was at 2, that's the x coordinate of Q. My x plus h value is 17, so that's all the way over here. And the distance between 2 and 17 is 15. So that's my h, that's my change in x. And so there's the slope of the secant line. Well, what I want to do is find the slope of the tangent line at point Q. So to do that, I take the limit of the slope of the secant line as h, which is the change in x, approaches 0. And graphically what happens is that forces those 2 points to come together, overlap, and that creates my secant line. With this third demonstration, I wanted to show you that h could come from either direction now. H doesn't always mean it's on the right, it's just some change in x. So here my h is negative 2.25, because I slid point P over here to the left of point Q. So my x is 0, and my x plus h is negative 2.25 since I slid left. And I'm going to make that h value come closer and closer to 0, meaning the change in x is now approaching 0, meaning there's no change in x. And then once those points overlap, bada boom, bada bang, I've got myself a tangent line. And I am now able to find the slope of that tangent line, which is synonymous with instantaneous rate of change, which is the same thing as the derivative of the function at point Q. Before moving on to some examples, I need to show you an alternative definition, one that is used by a lot of software programs to find the derivative. For example, our graphing calculators use this definition to find the derivative, and it will show up on my test, on other AP tests, or on the AP test. And it's very similar to the formal definition, but it's coming toward the point in question from two different directions. So we have f of x plus h to the right of x, and then x minus h to the left of x. And so we're looking at that change in y over this change in x, which would actually be double what it normally is. So it's the same premise as the other ones, and that is I'm trying to find the slope of the line tangent to that point f of x, of the curve f of x. So this time, instead of just moving to the right and then sliding it back toward x, I'm going to have a distance of h on the right, which would bring me over here to x plus h, and then another same distance of h on the left, which would bring me over here to x minus h. And so I'd have this point right here, which would be x plus h, comma f of x plus h, and then this other point over here, which would be x minus h, comma f of x minus h. And instead of just sliding one point toward x, both of these points would be sliding toward x. And so my overall change between those 2 points is 2 h's, double the h's as before, because I have this h and that h, and that's the overall change between these 2 points. And they're coming together toward the middle, toward their average. So it's kind of like finding an average right here. Change in y over change in x, and then you take that average as h approaches 0, meaning there's h is getting smaller and smaller and smaller and smaller and smaller and smaller on both sides, so then you end up approaching x basically. And so that is equal to the slope of the line tangent to the curve at x, or f prime of x, or derivative of f at x. So I need you to, along with the other two, memorize this definition, because you will have to recognize that as a derivative. This in your mind has to also be the same meaning as this, and the same meaning as this, and you need to be able to recognize all 3 formulas as derivatives. So we'll move on to our first example. Now, as a class, we're going to work primarily with the first 2 definitions. So that's what this first example wants us to try. And so here's my curve, f of x, and for the first part of this, let's go ahead and attempt to find the derivative of f at 2, or the slope of the line tangent to this curve at x equals 2. According to that definition, I would need to find the limit as x approaches 2, because now I'm going to basically replace a in the formula with 2. So x is no longer approaching a, it's approaching 2. And then I have f of x minus f of 2 all over x minus 2. Well, as we know, f of x is x squared plus 3x. So that's really x squared plus 3x minus f of 2. So f of 2 we could find by plugging 2 into the f of x function, so maybe I'll do that off to the side here. That would be 2 squared plus 3 times 2, so that would be 4 plus 6. So f of 2 is basically 10, so then I'm going to subtract 10. And then I'm going to divide that by x minus 2. So I need to find this limit. So the first thing I'm going to do is try substituting. So I'm going to plug 2 in here and here, and when I do that, I get 0 over 0, which we have now been trained. That doesn't mean we stop, that just means we need more work. Needs more work. So I'm going to go ahead and try factoring the numerator. So I have limit as x approaches 2 of x squared plus 3x minus 10, so that's a polynomial. I'm going to try to factor that into 2 binomials, hoping that one of them is x minus 2, so in fact maybe I'll start with that. Well, then I'd have to have an x here, and I'd have to have a 5, because I need x times x to give me x squared, and I need 2 times 5 to give me 10. So let's see if the whole thing works. So that would give me x squared, that would give me 5x, that would give me negative 2x, and so 5x minus 2x would give me 3x, and then that would give me negative 10. So that has worked. So now we're going to basically cancel out the 0 over 0, and I'm left with finding the limit as x approaches 2 of x plus 5. I plug the 2 in, and I get 7. So what that means is the slope of the line tangent to this curve at x equals 2 would be a slope of 7. So let's just, for learning's sake, take a look at the graph and see if it looks like we are on the right track. So let's go ahead and sketch the graph of f of x, which is x squared plus 3x. And let's use a standard viewing window. And then if you look, let's go ahead and trace over to 2, I guess. So I'll go until it says x is about 2, it's like right there. I'm already off of the window. It's already, the y values are already above my window. So let's have the y max go to 15 so I can actually see what I'm doing. And so let's do that again until x is about 2, like right there. If I were to draw a line tangent to the curve, it is a very steep positive line. It looks very likely that that slope would indeed be 7, which tells me that we probably did that right. Okay. So that was one particular slope at one particular point. But supposing I wanted to find the derivative as a function, I wanted to find a whole collection of slopes of tangent lines, not just one, I would use the formal definition to go about doing that. And that's the definition that says take the limit as h approaches 0 of f of x plus h. So we're going to have to really use our algebra skills here of substitution and all that stuff, minus f of x all over h. Okay, so that means I actually have to plug in this binomial x plus h wherever there's an x in the original equation. So I'm going to have x plus h quantity squared plus 3 times x plus h, because that's f of x plus h. So all of that minus away or subtract away f of x, which is just x squared plus 3x, all over h. So now let's do some simplifying. I need to FOIL that, I need to distribute that, I need to combine like terms. So when I FOIL x plus h squared, I get x squared plus 2xh plus h squared. When I distribute the 3, I get 3x plus 3h. And then when I distribute this negative, I get negative x squared minus 3x, all over h. Well, right away, I notice these x squareds cancel. I notice these 3 x's cancel. And I'm left with, and I'm running out of room, which is frustrating, so if you don't mind, I'm going to flip this over to the back. I am left with the limit as h approaches 0 of, let me flip back and see what I had, 2xh plus h squared minus 3h all over h. Or maybe it was plus 3h, just kidding. Well, again, if I try to substitute in the 0 for h, I would have 0 over 0, which, as we know, means it needs more work. So I'm going to go ahead and factor out the h in the numerator, and I end up with 2x plus h plus 3, all over h. So nicely, the 0 over 0 cancels out again, and I'm left with the limit as h approaches 0 of 2x plus h plus 3. So I plug this 0 in where the h is. I don't do anything with the x because this can almost be thought of as a constant, because I'm taking this limit with respect to h, so x means nothing. H is the thing that matters. So I plug 0 in there and I get 2x plus 0 plus 3, which basically equals 2x plus 3. So that right there is f prime of x, meaning I could plug in any x value into here, and that would tell me that particular slope of that particular tangent line at that particular point. Let's see if it works with the first one. So the first one was f prime of 2, and we got 7 when we wanted to find f prime of 2. Let's see if that would work here. So if I plug in 2, I get 2 times 2 is 4, plus 3 is 7. That's a check. That means I have the derivative of f at any x. I can plug in any x and get the correct derivative at that point. So with that idea, with the idea of a function, the derivative as a function, meaning a collection of all slopes of all tangent lines at a given point x. We're going to take that one step further. We're going to look at another GeoGebra video or demo with that in mind. So we're going to investigate further the concept of the derivative as its own separate function. So let's begin by entering in an equation here. I'm going to go ahead and find the derivative of this function y equals sine of x. So here's the graph, here's the equation. I'm going to first begin by putting a point on this function. Okay, so that point I can see that if I pick it up and move it around, it's attached to this curve. It's not going anywhere other than the curve. So this point A contains all the x values in the domain of this graph and all the y values in the range of this graph. Now I'm going to go ahead and put a tangent line on this curve. So the tangent is going to be tangent to the curve of f at A. There's my tangent line. Okay. Now if you notice, I now have an equation for this tangent line here, and the slope of this tangent line is equal to the derivative of the function at that point A. So what I want to do is put together a whole collection of all the different tangent lines at all the different points, so that when I'm looking at whatever the point may be, I could then find the derivative at that point, or the tangent line at that point. And if you look, I have a collection of all kinds of different slopes. Some slopes are positive, like right here. Sometimes the slope is 0. Sometimes the slopes are negative. And I want to put together a function that would have all those collection of all those slopes of all those tangent lines. So what I'm going to do is I'm going to now create another point where the x-coordinate is the same as my point A. The x-coordinates are no different. And the y-coordinates are the slopes of this line here. They're the slopes of the lines tangent to the function at A. So I'm going to type in slope of A, because that's the name of my line. Okay, so, whoops, I have too many brackets here. Okay, so this point B down here, right now it has the same exact x-coordinate as A, the point A does. So it shares the same x-coordinate as the curve y equals sine x, but its slope value is a small negative slope. So notice here's the slope of the tangent line, which is now the y value of this different point. And what we're going to do is put together a collection of these points. So I'm going to turn the trace on for this point, and I'm going to keep track of all the different points for all the different, all the different points B for all the different places on the curve. So let's go ahead and drag point A around now. And as I can see, when I put together all those points, it's starting to form a function. In fact, a function we all know very, very, very well. So I'm going to go ahead and move this around so I can color it in there, make it nice and dark there. So now I hope you're recognizing what that function is, the function that we just traced in. That function is basically the collection of all the different points that share the same x-coordinate. Notice how the x's, the A and B, are always either above or below each other. They're at the same x value. Notice that. But the y value for B is the slope of the line tangent to the curve at the point. And so this is really the definition of a derivative. A derivative is where you have the same x values as the original function. So B and A have the same x values. But the new derivative function, its range consists of all the slopes of the lines tangent to the curve at that point. So x values to the original function, the derivative, are the same. The y values of the derivative are the slopes of the lines tangent to the curve at that original x value. And I hope you're noticing that the derivative of sine is in fact cosine. This curve right here we know so well is the curve of cosine of x. That's the derivative of sine x as a function. We're going to prove mathematically what we just witnessed in the GeoGebra demo, that the derivative of sine of x is in fact equal to cosine of x. So we're going to try to find f prime of x for f of x equal to sine x. And we're going to do that by using the formal definition. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. And in this case, f of x is sine of x. So we're going to do sine of x plus h minus sine of x all over h. Now, if you recall from pre-calculus, we can't just distribute the sign. Sine is a function, and this is the argument of sine. So sine of x plus h does not equal sine of x plus sine of h. We have to use the identity, the sum identity from before. So let's just remind ourselves what the sum identity for sine is. The sum identity for sine says that sine of x plus h is equal to sine of x times cosine of h plus cosine of x times sine of h. Didn't make my memory bubble big enough. So that's what sine of x plus h equals. So let's write that all out. So I have the limit as h approaches 0 of sine of x cosine of h plus cosine of x sine of h. That's my sine of x plus h, and then all of that minus sine of x all over h. So we're going to have to get creative here in how we go about finding this limit, because if I plug 0 in for h, cosine of 0 is 1, so I'd have sine x plus 0, because sine of 0 is 0, so I'd have sine x times 1 plus cosine x times 0. So sine x minus sine x would give me 0, all over 0. So I have 0 over 0. So I need to do more work. Well, I do see a special limit. It looks like what could be appearing right there, sine h over h. And I see that this term has a sine x in common with that one. So let's see if I can finagle this around a little bit to my advantage. So I'm going to put the sine x over here with these terms since it goes together, and then I'll think of this as something separate. And it looks like we're going to have to move on to the back. Let me see if I can squeeze down here. Then I'm going to factor out a sine x that these have in common. And then I have cosine x sine h all over h. Then I'm going to split this into two separate fractions. So I'll have sine x times cosine h minus 1 over h separately, and then cosine x sine h over h separately. And I'm taking the limit as h approaches 0 for both of these. But I also know from the sum property of limits that I can find those limits separately, find this limit of this one, find the limit of that one, and then simply add them together. Well, what I notice are two special limits. I notice that I have my special limit of sine h over h, and that limit is equal to 1. So this is my special limit, that equals 1. So then cosine x, now remember I'm taking the limit as h approaches 0, so that does not affect x. So you kind of think of cosine of x as just a constant or a coefficient. Doesn't change as h approaches 0. So this becomes cosine of x times 1. So this limit here is just cosine of x. And then our other special limit from before that I asked you to remember was cosine of h minus 1 over h. That special limit goes to 0 as h approaches 0. So this limit is 0. So I have sine x times 0, which is still just 0. So these are my limits separately. Then if I add them together, I get 0 plus cosine of x, which is just equal to cosine of x. And so this, in a long, complicated way, proves without a doubt, without a shadow of a doubt, that the derivative of sine is in fact cosine, and we also witnessed that in the GeoGebra demo. Now I'd like you guys to go ahead and try this one. So pause your video here and start it again once you finish the question. So here's all my work for the U-try. There's my answer. I got -1/9. If you got something different, then you can take a minute to kind of look over my steps. If they seem like gibberish to you and you have no idea what you're doing, please come see me in tutorial. I'd love to walk through this problem with you.